what we want to talk about this morning, and I want it to be somewhat unidirectional right now, but I hope it'll be a discussion at the end, is what I'm calling how to move towards low input cleaning practices. And what I want to try to leave you with is maybe 4 different sets of things to think about. And the question is, to what extent and when might you move along a path which would get you towards one of all of those? I'm not interested in putting expectations on you. I'm interested in having you make some sense of what's available and what's changing and where the future lies. So I want to begin by looking at how to clean effectively, and that gets back to what the purpose of cleaning is and how to do it with low input chemistry and energy. In order to do a good understanding and foundation for talking about cleaning chemistry, it's important to understand how bugs get killed and how we refer to that as disinfection kinetics. How quickly can organisms be inactivated as a function of time and chemistry concentration, and what kind of chemistries do that, and what kind of chemistries do we want, and what kinds of chemistries do we want in discharge in wastewater. So that'll be the triangle I'll be trying to put together. And so we'll look at the disinfection kinetics. We'll look at an old reference model, which is it leads up to a line of understanding which says that the concentration that you have times the time that you have it in contact with the organisms is what determines the amount of disinfection that occurs. And what the principle of it is, you can halve the time if you want to double the concentration, or you can halve the concentration if you want to double the time. So it means that if you're going to go back towards lower input chemistries, you would need to be looking at longer times to achieve things. And in the world of sustainability, that's not a problem. Usually we've got tons of time to get these things done. It's just that in the modern world we've come to this thinking where if we can do them in a second or a minute or 10 minutes, it's better than if it takes an hour. So it's trying to unwind that a little bit and say, it's okay, I'll take an hour, and in fact I might even take 2 hours. The question is, how do I set it up so that I can do it effectively in 2 hours so that I don't use nearly as much material in terms of chemistry. Maybe I'll get this warning every 5 minutes, we'll see. Talk about the organisms that are typically used in cleaning sanitation chemistry versus what we're interested in winery microflora. Talk about clean in place, and clean in place is a technology that a lot of wineries and small wineries say that's well beyond what we need to do. It's only for big places. What I'll try to explain to you today is that actually it's probably more beneficial in small places, because you really want to be able to capture the water after you've cleaned the tank and not have it go down the drain. And the essence of being able to do that will be having a cleaning system that lets you capture the water before it goes down the drain so you can reuse it. A little bit about wastewater, BOD, biological oxygen demand. When we use different choices of chemistries, often that results in more effort and energy and time in a wastewater treatment. So the question is, could you have cleaning chemistries that actually don't contribute to sorry, I'm trying again here. And the other thing in our cleaning chemistry is not just that it takes air or it takes energy to break down the organic component into oxygen and CO2 and other things. It's about what's left over. And what's left over from most wastewater ponds that most wastewater engineers don't understand is the inorganic salts that we put in that weren't broken down by the BOD and the organisms. And those are typically phosphate and sodium. And so the real question is, why are we putting sodium back onto soil, and why are we putting phosphate into water that's only going to dam up somewhere and grow algae? So it's trying to go beyond traditional wastewater chemistry of cleaning agents and understand why we want inorganic chemistry that's also acceptable. Just a little few diagrams to try to set the stage. Up the top corner, we want to achieve disinfection. We want to clean stainless and we want to clean barrels. Today we could use a range of things from ozone to TSP, trisodium phosphate, with caustic. Some people are still using chlorine components. Some people have gone to peracetic. Some people are looking at chlorine dioxide. But the end result, that what goes out in the wastewater is going to be, we may have eliminated all of the BOD, but now we've got sodium in the water. Now we've got phosphate in the water. Now we've got nitrate. And these things are going to go onto our vineyard. Even if we want to use the water again, we've actually got significant impact from the question coming, why did you use the sodium? And where the hell does this phosphate come from? And why are we putting more nitrate onto vineyards? And that's because we think we're smart by using wastewater, but we're not smart enough to change the chemistry upstream so that we can use the wastewater without these complications. So the four things I want to leave you with are the four corners of this diagram. The microbial disinfection and the stainless and barrels. And we want to kill the bugs we're worried about on those surfaces. On the top right-hand corner, we actually want to use the least amount of water. And part of that's related to our winery practices. And we can come back to that in question time. But the problem that many winemakers have is doing things which require them to take wine from one tank to another, or from a tank to a barrel, or from a barrel back out of into another barrel. And every time we do those transfers, we have to use water to clean. So the question is, why do we do those transfers? Because if we didn't do some of them, we wouldn't do so much cleaning, and we wouldn't need so much water, and we wouldn't generate so much wastewater. So part of the low input thinking is going to have to be how we change the practices, but also how we could maybe use the water a second time in the same process. Not just put it out to vineyard and pasture, use it in the same application again. Bottom left-hand corner is, we'll see in a minute, one of the things that's quite effective is simply hot water. And the question now is, why are we burning natural gas to make hot water? Why don't we simply capture that in terms of solar hot water? And what temperatures do we need, and how do we store that? So that we could have a hot water capability, but not with much energy input. And then the last one in the bottom corner is how to eliminate the inorganics from our wastewater exit stream, as well as the BOD and COD of adding organic sanitizing components. So what I want to leave you with is the centerpiece. What can hot water do to kill bugs? What does hydrogen peroxide do to kill bugs? How we could use potassium buffers that give us pH 11.5, which peroxide is still 50% active at. And how do we use potassium bisulfate, which is pH 2.5, that's also lemon juice, and peroxide is very effective at that pH as well. At those two pHs, no pathogens can grow. So not only are those solutions sterile and stable, when we go to clean, we've got no concern about pathogen growth in those environments. And the last one is, if we made up those solutions of fairly clean water with potassium buffers that are very dilute, and we added peroxide and we killed everything in the time we wanted, could we take that water, filter it, and use it again? And so it's that last bit that relates to the water recycling in the winery, not just in the vineyard, that I want to cover. So let's jump quickly to models for how bugs get killed and try to understand the time and the concentration of a chemical when we talk about killing organisms or decade reductions in the viable population that's in a barrel or on a surface film in a tank. Here's a set of equations, and all I want you to focus on is the top one, which is the simple one. And so there are various descriptions for various kinds of chemistries on various kinds of cells, whether they're cysts or virus or bacteria or yeast. But the simplest one is the top one there, which is Chick-Watson, so-called Chick's law. And what it says is that the ratio of how many bugs are alive compared to how many were alive when you began, the rate at which they get killed is determined by the concentration, raised to some power, times the time. And that's the CT value, we call it, the concentration times the time. And for a particular cleaning chemistry, such as, say, chlorine in the old days, it follows Chick's law very well. And the implication of Chick's law is, provided the product of C and T is equal to some constant, or some number, you can double the concentration, and it'll take you half as long to achieve the same thing. So the same amount of killing, it's just that if you doubled up your concentration, you halve the time. And what we want to do is go the other direction. We actually want to take more time so we can use lower concentrations and still achieve the same killing. Okay, so that's the basis of the killing concentration time kind of thing I'll be talking about today. It's how do we allow more time to do things with less chemistry. And it's the fundamental of this sense of Chick's law that I want you to understand. So the rate at which they die depends on the concentration times the number of cells. In Chick's law, that's raised to the power n, but typically in the case of chlorine and a number of other agents, that n becomes 1. So it just becomes single concentration active. I said active is the concentration because things like ozone decompose. So the concentration that's active keeps changing. But things like chlorine or peroxide, their concentration stays constant. So it depends on the kind of agent we're using is whether the concentration stays steady or whether it falls away. But typically we follow that kind of law. Down on the bottom of the screen, the logarithm of the number of cells that are alive right now compared to the number we had when we started is related to the concentration we're using and how much time since we began. Okay? And what we want to understand is what's the term on the left? Do we want the number of cells to be 1/10 of what we had when we started? Do we want it to be 100th or 1,000th? So we'll come back to talk about how extensive do we want the killing to say that it's clean. But if we knew that and picked that number, we could work out how long in time and what concentrations would work for us. So just a quick recap, it's the CT value that I want you to understand and why in the low input world we wanted to reduce the nature of the nasty chemistry we're using to go to simpler chemistries, and we want to understand what's their relationship with concentration versus how long it takes to get the same thing done. So we'll talk about what we call log reductions. If I had 100 bugs and I killed 90 of them, so I had 90% of them eliminated, we call that one log reduction. We went from 100, which is 10 to the 2, to 10, which is 10 to the 1. So if we had a one log reduction, we'd have got 90% of them killed. If we had a 2 log reduction, we would have gone from 100 down to 1. That is 90% of them would have been killed, but that would have been 2 decades. 100 is 2, 1 is 0, so that's 2 decades reduction of cell count that would have to be achieved. Some food systems talk about 3 log decades or 3 log reductions, and some people talk about 4. The challenge for us is, since we're not under the food regulations, or in some places we are, the people in dairy and foods often talk about 3 and 4 decade reduction as their criteria for cleaning. And unfortunately in the wine business we're not very good about saying what we think that number should be. So let's try to think of something that's more like 2 and 3, not 1 reduction, and let's think that maybe we could go to 4 if we had to, but we'd go there if we really needed to, but we probably don't need to right now. So our interest is in less input. We want to understand how contact time affects that. I'll give you the chlorine example to demonstrate it, but I'm not going to suggest we use chlorine. I just want to use it as an example. So here's some old data for The axis on the left-hand side is the number of bugs that are alive, surviving, compared to the number we started with, and it's a logarithmic scale. And across the bottom is a function, which is 1 plus something times CT. It's effectively the time scale. And you can see all of the points, which is all of the data collected for how long it took to get a certain degree of killing on the left-hand axis. And what it turns out is that the killing function is a straight line. And the slope of that line is related to the concentration times the time. And so if we followed the chlorine example, the little dotted line there that shows 2 by 10 to the minus 5 survivors says that we would get something like, in this example, maybe 38 on the horizontal axis. And if I calculated back to that, if that's the degree of killing I wanted, there's a range of compositions and times which multiplied together would give me the 38. And so for any degree of killing on the left-hand side, I know what the concentration times has to be, and now I get to choose what strength of solution, and from that, how long I have to have that in contact with the surface to kill the bugs I'm interested in. And again, what we're interested in is moving towards lower concentrations, and it's important to understand that that's going to take longer to get the same degree of killing. But that's perfectly okay if we want to have low input. And here's another way of plotting it, just as concentration on the left-hand bottom axis and contact time on the left side. And you can see now that in the table, different concentrations and different killing times to get 90%, which is the 2-decade reduction. So if I had 0.05 grams per cubic meter, it'd take me 16 minutes. If I wanted 0.14, it would only take me 4 minutes. What we're interested in is going towards the 0.05 or the 0.01, so that it might take us 45 minutes, but I'm using a 10th or a 100th of the chemistry. Okay? So trying to understand how the sanitation chemistry works, trying to understand this concept of concentration and time, now can we go and look at more general chemistries that might be possible? And that's where we want to go forward. So to give you some idea of why Chick's law isn't always the thing to use, we'll look at ozone. So here's some example of, on the left-hand side, the initial ozone concentration, and here's the contact time. So there are a lot of people that are using ozone, and a lot of people who misunderstand ozone, but what it shows here very clearly is the ozone that you make usually isn't around 10 minutes later. So the sense of ozonating water to clean a tank, I want you to realize after 10 minutes you have no ozone left. The water is sterile, you sterilized it, but it's not a solution which is going to sterilize your tank because there's no ozone left. Okay? And what happens with that, this is the killing kinetics now. So here's the log, the number of cells that are viable versus the initial, and across time on the linear scale on the bottom for different levels of ozone. And so if we wanted a 2-decade reduction, like we talked about, we would start at 0 and we'd go to -2. And according to this graph, you would need 0.5 milligram per litre. And for the first 10 to 15 minutes, you kill everything. But after that, you don't kill anything extra. And the reason for that is the ozone's all gone. So as you go to higher concentrations, and you have to go to higher concentrations if you want to get 3-decade reduction, which would be going from 0 to -3 on the left scale, or 4-decade reduction if you wanted to get to -4, you realize that you're going to have to use 3 milligram per litre or higher ozone. Now, as you know, in the industry, most people don't use those levels. They use smaller levels. And what I hope you can understand is that typically we'd be lucky to get 2-decade reduction with ozone. And we might say we killed everything, but what we really did is we killed 99% of the bugs that were there, not all of them. And so that's an example of a compound which decomposes, has a limited lifetime, and if we don't get the killing done in the time available, nothing further happens. So We're not interested in ozone because it's a pretty nasty material. We're interested in things like peracetic acid, PAA, and a number of you may be using that already. You can also buy peroxycarbonate, which is the carbonate ester instead of the acetate ester of it. Those of you that have seen obnoxious TV commercials for OxyClean, that's what peroxycarbonate is. The problem with PAA is, as you understand, is when it breaks down, it releases hydrogen, peroxide, which is terrific, except you get a residue of acetic. And most people don't like acidic smells in wineries, but it's a bound form of peroxide. The other feature of it, as we'll see later, is it has a BOD contribution in the wastewater because of the acetate. And so the question is, could we just use peroxide? And now we want to understand how the peroxide works at different pHs. And then the ultimate question is, could you get away with just using hot water? And now what we want to understand is what happens to hot water if we change the pH. So these could be very simple chemistries, very dilute buffers, and the question is, can we add peroxide or not? And what can we kill with hot water alone? So there's two papers that I'd made reference to. One of them's in 2008. It's actually got some disinfection kinetics for peroxide. It's looking at E. coli in particular. And it has a model, which is one of those models I showed you before, but don't worry about that. It's one of the few papers that addresses killing bacteria with peroxide and how long you have to take to get there. The other one is by Cerf and his group, which was looking at thermal inactivation, just hot water. What happens when you use hot water at different pHs in killing, again, E. coli, but they came up with a function which allows for the pH and the temperature on how it kills. And that's very helpful, as you'll see in just a minute. So we want peroxide because it decomposes back to oxygen and water. There's no organic residue, there's no chemical residue, and there's no significant health hazard in inhalation and exposure at the levels at which we're talking about. And that's not true of any other cleaning chemistry we use. So it's probably the most benign, and probably, because it's decomposing, the most environmentally benign as well. So it doesn't contribute sodium, it doesn't contribute BOD or COD to our wastewater. It's not difficult to, most people have a 3% solution in their medical cabinet in the bathroom. So it doesn't explode, it doesn't give you all sorts of problems. We often use it on open cuts. It's an antiseptic. And so if you go back to Labasse's model and you plug in values for different levels of peroxide, the model work was done at pH 7, but this is the graph that you get, and across the left-hand side is the log reduction. So if we start off with 1 and we go to 0.1, that's 1 decade reduction. And if we went to 0.01, it's 2 decade reduction, so it's 99% killing. And if we went down to 3, it'll be 0.01, and we went to 4 decade, it'll be 0.01, 0.001 at the bottom. And you'll notice, first of all, the time scale is in hours. So what that says is if we want to kill E. coli in pH 7, and we want to use, let's say, 500 milligrams of peroxide, which is half of a gram per litre, which is a 0.20%, it would take us about 5 hours. And most people say, well, I don't want to spend 5 hours cleaning my tank or my barrel. I want to get it done quicker than that. So, okay, let's jump to 1,000. And in 1,000, now the question's going to come, do you want to get 90% of the bugs killed, in which case it's going to take about 40 minutes, but very simple chemistry. Or do you want to go 2 decades? It's probably going to take you an hour. Or 3, maybe an hour and a half. Or maybe 4 decade reduction. It'll take you 2 hours at room temperature and pH 7. So we'll come back to talk about it later, but there's two concerns about what I'm talking about in time. One is the time that we actually spray the solution or have it soaking, and the other is how long the surface is wet. So if we wash a tank and we spend 10 minutes washing it, the real question is how long does it take to dry? Because the killing chemistry is still working while we're drying. And so if you washed a tank out, probably an hour later it might have dried out, depending on the humidity in the room you're in. But in many cases it's still wet an hour later. And as a result, it would still be killing, even if we took the solution away. So the point is, we don't know what criteria we want to use on the left side. Let's say it's 2 decades. At 1,000 milligrams, which is 10 grams per litre, which is 1%, which is a third as concentrated as the stuff you buy from the pharmacy or the drugstore. And that's got the capability to kill in an hour or so, based on E. coli. But ambient, pH 7. No buffers and no energy to heat. Let's go look at the water condition, because this is another interesting one to do. And the point now is we can get to 60 degrees Celsius or 150 Fahrenheit. You can get to that temperature easily in a concentrated solar hot water maker today. So let's look at 60, not steam, but 60, 50, and 40 Celsius, 100, 120, 150, something like that, Fahrenheit. But again, if we can just understand what water does, let's see what happens if we could shift the pH a little bit with some buffers. So this is Surf's group. This is looking at the speed of killing on the left-hand side and the pH. And you'll notice as you go to low pHs, the speed of killing increases dramatically, 10 times. And if you go to high pH, it also kills much faster. And this is based on E. coli. And this is based on 58, so we'll say 60 Celsius. So the point is, could we use water at 58 or 60? And we don't want to use it at 6. We want to make it 3 or 9. And I'll go as far as say, let's make it 2.5 and 10.5. And we can do that with the solutions I outlined before, which are just potassium-based, very dilute, and it will have fairly high killing power, just pH and temperature. So here's the survival curves. The bottom scale now is logarithm of time, but the left-hand scale is the same. It's the fraction viable. So each line is 1 decade reduction. So if we start off at the top, we go down 1 decade. You've noticed that at 40, it'll take us about 10,000 seconds. If we wanted to get down to 2 decade reduction, we'd have to go to 50 or 60. Well, let's go to 60. 2 decade reduction would take us about 100 seconds. That's just a minute and a half. So the question is, if we were trying to kill E. coli and we're only worried about pH 7, no buffers, we can get 99% of them killed in 2 minutes. So why are we using all this cleaning chemistry? If you plug into that equation and do it at 3, the curves shift a little bit. And if you go down to 2, we get down to here. So 60 degrees at 2, now in 100 seconds, I can get pretty close to 4 decade reduction. So that's enormous disinfection with pH 2 hot water. And it's not really, really hot water, it's just solar hot water. And so the question is that's terrific, except we don't have a whole lot of E. coli on our tanks. So the problem with these models is they're all based on E. coli for drinking water and for staph and a few other things in milk and dairy. And the problem is we don't have any data yet, almost nothing, that addresses Saccharomyces or Inococcus or Brett or Acetobacter, Pediococcus or Lactobacillus. And so we'll come back to the next steps, but the next steps will be trying to work out how sensitive are these bugs to temperature, pH, and peroxide. Because if we knew, we could go back and design a temperature, pH, and cleaning chemistry that would give us very good cleaning practices with very little chemical input. We also have to decide amongst ourselves, and we're probably not very good at that in the wine industry, of not talk about what good manufacturing practices are, or not what state-of-the-art practices are, but what's a real definition of what we want to kill and what level of sanitation do we want. So should we be using E. coli? We can for other people because other people are used to E. coli as the criteria. But we might want to look at not just bugs but mixtures of bugs. And the question is, how are we going to measure it? Are we going to measure it by swabs and ATP counts? Or are we going to do allow for the drying time as well as the contact time? And what's going to happen to that agent when we finish with it? And so that's what leads to the suggestions, which are trying to go inorganic rather than organic so we don't get the BOD and COD loads, eliminating sodium and chlorine and phosphate and nitrate, and switching to buffers which are potassium, and looking at hot water and pH and peroxide as the simplest and benign of the cleaning chemistries to achieve sanitation. So if we could make solutions which are 10 or 20 millimolar, very dilute, less than a gram per litre, pH 11.5 and 2, if we just had hot water, you can see that based on E. coli, that would be very powerful killing. The point about those solutions is when I mix them together, it's pH 7, neutral, and it's potassium sulfate, which is the most common of the salts in most groundwater systems. It doesn't affect plants, doesn't affect clay, anything like what sodium does. And so it's environmentally from a plant and a soil particularly useful, not acidic or basic when discharged, and without the other inorganic chemistries that we don't want. Just to give you some perspective, I'm talking about sodium versus potassium, the exchange in clay platelets in soils. So if you look at the hydration ion diameter on the right-hand side, you'll see the magnesium and calcium are the most easily penetrating into clay, which is why most clays are calcium and magnesium containing. If we put sodium onto those clay platelets in the soil type, we'll actually fragment them and rupture them. And as we go to sodium, there's a lot of swelling occurs. Notice that potassium and cesium are the least preferred in that series. And so, if anything, we want to put the least exchangeable destructive cation, and we want to use as little of it as possible, which is why the solutions will be very low in concentration. So we could go through various protocols looking at rinsing and capturing. The question is whether we're going to have the pHs different by those buffers, whether we're going to have peroxide, or whether we're going to have hot water. And we can use E. coli as our reference bug, but we probably need to do it for the bugs in question. I'll skip these two next ones. I'll put them in only in case of a discussion of how to calculate BOD and COD from the organics. It's only if people are trying to really understand why BOD in wastewater is what it is. But in an inorganic world, that would be zero. And that's the beauty of peroxide. There would be no BOD contribution. Just want to show you here that 100 milligram per litre of peracetic is going to give you a BOD of about 63. When we put it into PAA mixes, which you commonly buy, it's more like 300 milligram per litre. Now, compared to things like citric, that's a heck of a lot better, but it's still got a significant BOD load. And if we could choose a chemistry which didn't have that, that's why peroxide is so attractive. Just a shot of a clean-in-place system. This is the kind of thing you'd have in a winery now, so that you could use 3 solutions, so that you could recover them, and so you could filter them and use them again and again and again. And so at some point we'll start building small systems like this that recapture the cleaning water and use it many times. And that allows us to reduce our water footprint dramatically. And if we've chosen the chemistry right, the inorganic piece, we can use that over and over again as well. So we're trying to lower the water input, we're trying to lower the chemistry input, and we're trying to use our cleaning solutions many, many times. And one of the central pieces that enables that is a small CIP system. In terms of QC, there's different ways of doing it. We can swab surfaces, and the question is how many viable cells does your acceptable criteria. We can do total counts. We can talk about decade reduction. The trouble with the swabs is they don't work too well in barrels. So how do we measure barrel inertness? And when do we worry about bottling and when do we worry about tanks? There are various ways of measuring activity, and ATP is a measure of activity. So luminescence of ATP is useful in things like barrels where it wouldn't necessarily be a viable swab. There's a whole range of different chemistries, one of which is the riboflavin test, which on stainless tanks works pretty well. And whether we spray with riboflavin and then expose to UV light, what happens is you see this green solution that tells you that you didn't have much coverage. The other piece of the water one is if you could use very soft water and you only used it in your cleaning regimen and kept it in a contained loop, as you sterilize it and filter it, you could use it again and again, and because it's very soft, you won't need softening chemistry or ion exchange. You will be able to use the water on a membrane system and recover the water very well. And so now the question is, if you're going to use your solutions over and over again on a RO membrane system, you want to start off with rainwater because of its chemistry. And so now can you incorporate rainwater capture, very easy sterilization by membrane, very little chemistry input, very little energy input, and still kill bugs and use the water many times. And that's essentially what we've been trying to talk about. Just want to leave you with this metric or graph here. It's showing what happens if you can recover 90% of the water each cycle. So say we had a cleaning regimen and we had a CIP system and we used 100 liters or whatever to clean a tank. This is what would happen if we used it over and over again. So if I did 10 cycles, I'd use 1,000, 10 times 100. But if I can recover 90%, all I have to do each time is do the makeup. So instead of using another 100 the second time round, I can use 90 of the first lot, and I only have to add 10, and I've made it back up to 200. So by the time we go through 10 cycles, you've used 90 liters extra compared to what you would have used, which would have been 900. And so now you can use the water many times, and the use number there is more like 6. If we're using it 6 times over, what that means is I only use about 1/6 of the water. Now it's reasonable and possible to capture rainwater because I'm going to use it 6 times. It's 6 times more valuable than the same volume of groundwater or bore water or city water. So imagine if you captured on a roof and you stored your rainwater tanks and you were able to filter them into sterile RO water over a period of time. You could run a loop in the winery, which is completely sterile water for all of the things you use, and make up your cleaning solutions in the lab and everywhere else without deposits and yet sterile, without chemistry. In clean in place, we'd make up our solutions like we just talked about. We would rinse our tanks, and what comes back would be the dirty versions of those solutions. We'd keep them separate. We'd filter them on a cross-flow and a nanofilter. We would put the organics to a biodigester and produce biogas. And the inorganic 90% is what's returned for the next use, returning both the chemistry and the water. And then hot and cold water systems. There are solar collectors, which are concentrators. There's a company called Cogenera that does this kind of thing, sits on the roof and makes hot water, and makes hot water up to 60 or more. We're going to use a system which only goes to 50, but you could make 60 in that system. The one on the right-hand side is our chilled water system, which is not so important for this discussion, but it has to do with solar ice making as a chilled water system. So we need to understand the kinetics, and the wine research community hasn't done a very good job. Maybe I'd suggest to say, for those of you that know me, the wine research funding organisations haven't done a very good job of doing projects which would address these issues. Because if we'd done these studies, we would know these numbers. We could have talked quite specifically about killing a Acetobacter or Brett. Could we do it with hydrogen peroxide and pH? Or could we do it with pH and hot water? And I think you'd agree both of those alternatives are streets ahead of the current regimen we use for cleaning and disinfection. Can we recover the solutions over and over again? We don't have to do 90, even a little bit would help. And can we begin to put in small clean-in-place systems that make it really easy to cover the solutions so that it's possible to use them over and over again? It's an enabling piece of equipment, not a thing of it end of itself. So we want to use green cleaning chemistries, and it's a term I don't often like to use, but I think you would understand why it's low input and simple chemistry. We want to use potassium-based buffers. We want to use peroxide and hot water. We want to be able to recover them. We don't want to add to the BOD, and we don't want the solution chemistry of sodium and phosphate going into the vineyard. But we need to get this disinfection data for the bugs that we're particularly interested in. So I just want to close by thanking Abby and the organising committee to even take the step of asking me to do this. I realised being there in presence would be a lot better, but I hope this has been a convenient delivery for you today. And I'm very appreciative of the opportunities I get to do the things I do. Much of that's due to the endowment I hold within the Department of Enology. Stephen Scott, Chair. So thanks for your attention. Let's look at questions and discussions that can come up from your interactions.
So we're now off mute if anybody wants to start with some questions, but I'd recommend getting a little closer to the speakerphone. Anybody wants to sit here?
Hey Roger, it's Tom Fitzpatrick. It's good to see your face.
Yeah, I hope you didn't, but it's unfortunate, but okay. Thank you. Good to hear from you.
Just a quick question for you. The Chick-Watson relationship where you're looking at concentration and time, if you had sort of an example where you were sort of focused on decreasing concentration and increasing time, it seems maybe like agitation or mixing might be something that could increase the probability of sort of interaction between your sort of microbe in question and your agent in solution. Can mixing or agitation change that relationship?
No. So this is not mass transfer control. This is getting in it's the chemistry being delivered to the bug and how long it gets to get into the cell and how long it gets to kill the bug when it's getting into the cell. So it's not delivering it to the cell surface, which the mixing would help. That doesn't seem to be the limiting factor. If it did, we wouldn't get the kinetic expression that we get. So it's mixing more won't make this happen any faster. The slowest step is the rate-limiting one, which is the killing of the bug. So it's kinetically controlled by the killing chemistry, not the mass transfer to get it to the surface to get the killing done. Does that make sense?
Yes.
And it's but the sense of concentration and time is could you still kill them in just the same way if you were prepared to wait a bit longer? You can do it with a lot less chemistry. And so that's the principle I want you to get. The example with peroxide doesn't follow Chick's law very well, but it has a more modified, it's one that has other mathematics that I showed in that table. It has similar concepts to the CT value, which is why I keep using it as a model to learn from. But you can see from the graph of peroxide killing, the stronger we make the peroxide, the shorter the time is. And we know those equations, they're just not exactly the same as Chick's law. But the general principle is true. If we wanted to wait longer time, we could have got it done with less peroxide. And that'll be a bit of a, it's not a magic number, it's going to be an optimum. Different people might choose to do shorter times and some people might choose to take longer times. What we've got to be sure of is the times we choose are actually determined by the physics of the killing so that we get the same result.
So, Roger, this is Don Crank, and I was wondering if you would talk about the relationship between, well, oftentimes in wineries we're using water and sometimes chemicals to clean as opposed to disinfect. And you mostly just talked about disinfection, but I think to Tom's point, there's some degree of agitation and mixing that can help with the cleaning, although I don't think you really covered that yet, so if you would comment on that.
Oh, that's okay. No, yeah, so to me the cleaning issue is easy. Well, we could have a conversation about it, but it's not a problem. The reason we use spray balls in tanks is to clean the walls effectively with high-pressure jets. Now, we may pick up a hose and put our finger over the end and squirt it down and wash the wall, and you can do that. It's just that you won't get near the impact that if you had a small jet at a high velocity close to the surface. So using better spray devices to give you high-pressure rinsing, what we typically do in this example, and what we'll do here at school, is we'll actually do a high-pressure clean water spray to get all the pulp, the biofilm off the edge, the sugar solution or the wine solution off the wall, and the yeast in the bottom, and we'll flush those out into a separate container. And then we'll go back and sanitize. So it's important to do the physical cleaning before you do the sanitizing. What typically has been the practice, and unfortunately most of the cleaning companies are telling you this, is you do them both at the same time. What you just need is the magic cleaner, stick it in, spray it on the wall, and it'll both physically clean and kill. And you probably hopefully realize that there's two different functionalities, and maybe we'd be better doing it in two different ways, each of them very well, that aren't necessarily, the combined way is necessarily the best. So physically cleaning is the issue. If it's simply wine residue and grape juice residue or pulp and yeast, a spray ball at high pressure will take care of that in a few minutes. In barrels, it's now a question of why, I'll ask you the question, why do you have the sediment and the crystals either in your tank or in your barrels? If you weren't doing Surly aging deliberately, putting solids into a barrel that you then have to blast to get it back out again doesn't make a lot of sense in cleaning. And so if there's no good reason for having them there present, and there may be in some styles, shards for example, but I'm not sure that's the case with many reds, if we were to reduce the solid load we put into a barrel, we'd have a lot less time physically trying to clean the barrel so that it would be easy to do the sanitizing. And most poor sanitizing of barrels is limited by poor physical cleaning ahead of time. So the physical cleaning is an issue. It's just that we should recognize what it is and do it very well. Do it ahead of time, not try and do the two things together. The killing only needs the liquid to be flowing over the surface. So when we do CIP sanitizing, we don't want to be spraying at high jets to the wall necessarily. All we want is to flood the wall and to be trickling down the wall across the bottom. And so how do we get it up into the roof to spray the roof, trickle down the wall, and collect on the bottom and out the bottom of the tank? And now, if we've got clean surfaces, that's relatively easy to do. So the physical cleaning is the practices piece. And transferring tank to tank and doing all the things we do, like dump in bentonite and fining agents and other stuff, and then transfer the tank to another wine, to another tank, all of those practices are going to have to change in the future if we want to use less water. Because it's like going to a buffet and taking a clean plate every time you go back. Now, I'm not suggesting that you go back to the buffet 10 times. Some people will, but I'm suggesting that even if you went 3 times, would you pick up 3 plates? Well, if it was the food and sanitation master of the kitchen of the government health food office, I'm sure they would. But for you and me, we would probably use the same plate within an hour and not be worried about it. So we've got to understand why we use so much water, and that's somewhat tied to our practices. And part of that's the things we do in the first place that actually requires us to change the tanks, that requires us to do the cleaning. So that's a different discussion, maybe for another day. But If you think about how many times you transferred one of your wines this year, I suspect it's more than 2. It's probably more like 6 or 7, depending on whether you blended, might find, did a protein fining, did chip or wood contact, went in and out of barrels, and did a blending and did a bottling. The only question is, why did it take you 7 cleaning operations to do that? So our practices may be traditional, but we might want to think about that in terms of the future of water. But it is, no doubt, the physical cleaning is an important part, but you can do that with pressure and water. You don't need any chemistry to do that. And if you do, we should have a conversation about why do you have the chemistry requirement in the first place. So let's do some other questions first, and then if you want to, we can come back to that one, because there's an aspect of winery design and operations which has a lot to do with whether we get tartrate build up inside tanks, is whether we need hot caustic to dissolve it off. And I'll ask you the question, why did you build up the tartrate in the first place?
Thank you, Roger. I think we're going to break for lunch. And
okay, that's good.
If anybody has questions they had that weren't addressed, I would be very happy to take them and share them with Roger. But thank you so much for your time. Thanks, Roger.
That's a pleasure. Thank you.